let's have a quick recap of what we have learned in the first session. Okay, so I would like you to do the recap. One person will speak about only one point that we covered in the last class. So this is how we do it in the class, that sometimes I give the recap, but to check that the students have gone through the previous notes, I ask the students to do the recap. Yeah, so Ankit, you can go ahead and give one point about what we learned in the last class.
So we have a discussion about agentic AI.
Mm-hmm.
What agents are. We have a comparison between what is agentic AI and what is genetic AI.
Mm-hmm.
Along with we have generated SSH key and
Only one point. Only one point. Yeah, okay. Can anybody tell me that one of the discussions that we covered in the last class, we had some 5, 6 different questions and we had long discussions around those questions.
We discuss on about what is the difference between generative AI and agentic AI.
Generative and agentic AI difference. Okay, good. Then anybody else? Nitin.
Sir, what do you mean by intelligent agents, and how Ecodot is using the artificial intelligence?
Okay, okay, good. Anybody else?
We also discussed about different aspects on why and when we can use the traditional ways of coding and app development versus intelligent applications. And we discussed that there could be some specific use cases where the AI or these kind of applications could actually be helpful, but we cannot discount the fact that the traditional ways of developing the applications, they still hold true in certain situations. So we will have to evaluate the specific scenarios based on which we need to take a call whether we need to go for AI applications or continue with traditional ways of development.
Right. So we looked at that trust in the traditional software and how AI systems differ. We also looked at what Nitin has mentioned in detail and how the different kinds of applications that have come.
Yeah, we discussed about the setup of GitHub as well, right? The way we did the setup of the GitHub using SSH, and we did the setup of SSH also. Right, we understood about the usage of public key and private key for the GitHub. We entered that public key into the GitHub in one of the sections in GitHub under, I think, under security. Yeah, so I think those were the ones. We also used PowerShell. Yeah.
What was the real world analogy, the travel agent? Can anybody summarize it?
Also, we discussed about that the personalized choice of the family members. There might be multiple family members. They have their own preferences. So this kind of agents can take care of all those individual choices and preferences.
Right. So with the help of a real world travel agent analogy, we tried to connect that how the modern days AI agents are able to do the similar task what a human travel agent is able to do. So we don't go and micromanage. Similarly to AI agents also, we don't go and micromanage. We give our preferences, we give the task, dates, other contextual information, and then let the agent do its work. Okay, so that was discussed. We also started our session with the Alexa demo, and during that interaction with the Alexa, we interacted with the Alexa for 2 tasks. What was the first one?
No,
music.
Can you repeat the question?
Okay, we asked Alexa to do 2 of the tasks that Alexa is capable of doing. What was the first task?
Play music.
Who said music? Ankit? Okay. Ankit heard the music. Anybody else who heard something else other than music? Was that the music? Did I ask it to play some music?
News.
News briefing. Yeah, it was a BBC News.
BBC News.
right? And what was the second task?
The second task was to schedule a meeting in the calendar.
Yes, very good. Ahon is saying that the second task was I asked Alexa to add a meeting in the calendar, and then we verified that Alexa has done it correctly. And then from that conversation, we started looking back into that what just happened between us and Alexa, how Alexa was able to do it. So once we started drilling down into that conversation, connecting it with where is the AI in all of that interaction we had, and we came to know that lots of AI related tasks Alexa is already doing, but it is not that capable in the sense it lacks certain agency. For example, reasoning task, complex statements. If I have to tell about news, but I don't say the particular news word, I say something else, Alexa generally is not able to handle such kind of interactions. Okay, but this is still a remarkable piece of thing which exhibits that some autonomy is there and it is able to perform what we ask for. Okay, so that was about the last class review. If you notice that in LMS, in the first section, when you open the course, in the first section, I have written a couple of points related to how to get the good outcome from this course. So there are some points are written. In your free time, just go through those points and see that the first class review what we have done just now, recap what we have done, whether that recap would have been better if you just follow those points. So if you follow those points, would the recap, your ability to do the recap, would that improve or not? Okay, fine. As the cognitive science says that if any lecture is delivered and we revise it within 24 hours, first one revision in 24 hours and then the second revision in 7 days, it retains for a long time in our mind. Okay, so what we are going to do today? Today we will look at, before jumping into the agents, we will see that how we reach to the agent, the progress of AI, that we are capable of creating AI agents. So what is that technology journey? We will do a fast forward of that. I will not start from 1950s, 1960s kind of thing. We will start from a decade back, and then from there we will see how the things have progressed. Those who have interacted with, or those who have been in touch with the AI, they will recognize this thing, that AI today is able to help us do all kinds of things, like variety of things in business, non-business scenarios. It is able to do in different industry settings. It is able to do, but we reached here after a long years of continuous scientific development. There was a time where the machine learning systems, AI systems, were task specific. For example, if you have to develop a vehicle recognition model, then it will only do the vehicle recognition. It will not do some plant identification. If you take a photo of a leaf and identify the plant, it won't be able to do it. But if you take a photo of a vehicle, it will tell you that what kind of vehicle is this. So task specific models were popular a decade back. Okay, you can say that till 2012, 13, 14, task specific models we used to build. Now there was a whole lot of efforts that used to go in building task specific things. You have to collect large number of examples, example data. If it is text, then you have to collect hundreds and hundreds of domain specific text. If it is image related, then you have to collect thousands of images in different settings for a particular domain. If it is video related thing, then you have to get hundreds of hours of video for the particular domain or task that you want to develop the model for. It was a extremely painful process and used to take years together to develop the AI system. And millions of dollars were spent on developing task specific models. That journey got changed from 2012-13 onwards because of the two primary reasons. One was the change in the advancement in the hardware, the availability of GPUs. In 2012, with the LXNet, I mentioned it in the last class also. LXNet was a entry by Ilya Sutskever, Jeffrey Hinton, and one or two more researchers. They submitted that entry for the ImageNet competition. Basically, in that competition, the companies, the institutions, and the companies, educational institutions and the companies can submit their entries to evaluate their solution against the data set. So ImageNet data set is provided, and you have to provide your model to do the classification. And LXNet won that competition by a large margin. So the first and the winner and the runner-up, there was a significant difference. And one of the reason of that difference was that hardware, GPU. From there, the rise of deep learning started. Lots of companies started using GPUs. Okay. So the earlier world was task-specific model. How, if pictorially, if I have to show it, this is how the task-specific model training looks like. You have task 1, task 2, task 3, like task-related data. You are using it to model the task-specific model, and that can be used for that particular task. For another task, if you want to do, you will have to again gather the data, create its model, and that is so model M1, M2, Mn. These are all separate models. So task-specific models were highly domain-specific, costly affair, lengthy process, collecting the data. You might have heard the Amazon Mechanical Turk. How many of you have heard the Mechanical Turk or used it? No? Okay. So Mechanical Turk has been used by a lot of research groups across the world. It basically allows you to do the data labeling, data cleaning task. So you hire human labor, you pay them certain amount. Basically, they can bid, and then you give them access to the data where they have to do the labeling. So large number of groups across the world have used such kind of services to do the labeling. Okay. Now that entire thing got changed to another technique which is called transfer learning. This is the model of transfer learning. This is a very interesting thing that has happened in last 10 years. In transfer learning, basically you have data for one particular domain, a large amount of data you collect. Okay, a huge amount of data. Let's say millions of books and millions of websites have collected. That particular data is used to create a source model. That source model then gets translated into a trained source model. Okay, after training, so this is the training process happening, and then you create a source model. Okay, now this training process is done via deep learning. In the task specific thing, earlier the deep learning thing was missing. Because of that, the model that you are creating, M1, M2, Mn, all the separate models, they were only task specific models. M1 cannot do anything about M2. M2 cannot do anything any task related to M1. Okay, but in transfer learning, the training process involves deep learning. I will come to what is deep learning and how it differs. Now, because of that deep learning, your model, source model, learns the fine-grained details of converting the data to a particular kind of classification. Okay, for example, you have millions of images of different categories. You have animals, you have babies, you have toys, you have laptops, phones, vehicles, clouds, windows. So more than 1,000 categories in the ImageNet dataset. More than 1,000 categories of data are there, and in total about 1 million images are available, segregated into different categories. Now, once you feed those images to a deep learning model, I'm just giving you an example of how in the computer vision deep learning is used and how you can create a source model. So those images, let's say this mobile. How the training happens, there are large number of neural network layers are there. First layer, let's say there are 100 layers are there, and then the final output comes. So the first layer will learn only the edges of this phone. First layer will not learn the entire mobile phone. From the image, it will just consider, okay, there is a vertical edge, then there is a rounded edge, then horizontal edges, all the edges only. The next layer may learn the texture. The third layer. So every layer is learning some abstract representation of the actual object. Okay. What does this basically mean is that your model, every layer in the model has got certain skills, and those skills can be transferred to some other domain. Let's say instead of laptop, now I want to recognize the pen. So the skills learned in the first layer, second layer, third layer, fourth layer, they are still useful here also. Okay, they will recognize the edges, they will recognize the texture, the shape, etc. And then the final output of object recognition will come. This process of that creating a very large source model and then transferring the skills that are learned in that neural network layers to another domain for which you don't have too much of data. That process is called transfer learning. Okay, there is a movie where this kind of thing is reflected. Let me play that particular thing. It will concretize our understanding about this. So, how many of you have watched the movie Matrix?
Yeah, I saw it.
Anybody else who has seen? Nitin
Yeah,
has
I have
also seen. Okay, all right. So this is the.
Now it is able to. Yeah.
So if you see in this movie, Neo doesn't know how to fight. Okay, but the another guy, the Morpheus, he knows how to fight.
Sure.
You see, the skills are not actually with Neo doesn't know that how to fight, but in his brain, through the cassette, those skills were transferred, and then his neurons are trained to understand that new knowledge. Okay, so his brain's neurons are basically getting retrained with the new knowledge that he has got. That particular thing is called transfer learning. To actually acquire these skills, it takes several months, several years to get that kind of skill as the Morpheus is showing. But here Neo is able to get it in just 5 minutes. Okay, fine. So that is what happens in machine learning also.
Sorry. Vinay, can you just go back to the upper one a little bit? So this was okay. This is completely different, right, from what we
Yes,
had.
this is task specific thing.
Got it. Got it. Thanks.
Okay,
Yeah.
but later due to the deep learning, we are able to do the transfer learning. That knowledge learned in one particular source model can be transferred in another domain where the data scarcity is there.
Mm-hmm.
And this happened because of the large number of neural network layers that are present in the deep learning. As you increase the number of layers in the network, the time taken to do the training increases. And the GPUs basically reduced that time by providing the extremely high compute power. Okay, so deep learning became successful, even though the deep learning idea was available earlier also, but hardware support was not there. It makes sense? Okay.
Same example which you gave related to the previous images, how that image is going to use those large set of image, how it is going to use in the transfer learning.
Good, very good question. I was expecting this question and you have asked. Okay, we have here another image. You see the input. Input here is a elephant, a deer, a penguin. Then in the middle portion, we have the layers that are learning some representation of the actual object. So for example, the edges are learned here. Okay, then more shapes like curves are learned here. Then in the third layer, we see that more complex curves are learned. Every layer in the deep learning network basically learning certain abstract representation of the final object. Now in the transfer learning, what happens? There will be large number of those layers will be there, and When it comes to the final layer where all of these abstract representation are merging and creating a more realistic object, there I cut that source model. Cut in the sense, I say that those layers, the top layers or the final layers where the output is about to come, at that particular layer I will start retraining. Only to those layers I will retrain. So I will feed my data from here, I will feed the new data, but for all these layers I will not update their weights. I will say that don't make any changes while you are doing the training, don't make any changes to these layers. Okay, because these are the same skills I need for the another domain also. And just make the change to the final layer where your actual object recognition is happening, very close to the final object. For only those layers, do the retraining using my limited data that I have. Are you getting the point? See, if I let's convert it into an analogy. A 1-year child is not able to speak clearly. He can only speak limited words. His vocabulary is very small. Okay, then he grows to 2 years. He can speak little clearly and vocabulary is also increasing. Then he goes to, in the 5 years of age, let's say he goes to the school, he is able to say more number of words with far more clarity. Then from class 2 or 3 onwards, he will get fluency very fast. It took 3-4 years to get the fluency, but after that, that process of learning new things or learning new words becomes very fast. Even in the another domain also, the kid goes to the school, starts learning the school syllabus. But in 5 years he was at home, no school feeding was done. But when he goes to school, start learning because those skills which are required for the brain to process the information, they are already built. Alright, so far is this thing clear that a decade back from 1970s to you can say that till 2012-13, most of the AI systems were task specific. If you have built a AI system, you cannot transfer the knowledge of it to develop another AI system. But because of the deep learning, we got chance to build such a big neural network that every layer is learning something. Finally, at the output layer, we get the classification that this is an elephant, this is a deer, this is a penguin. That is at the final layer we are able to identify. But what is happening in the hidden layers, in the in between it is learning the abstract representations of the object. So that knowledge I can transfer to some other domain. That is what the transfer learning is doing. Now within the transfer learning there is a concept called fine tuning. That fine tuning we will be doing for the agentic AI also, LLM fine tuning. Okay, so within the fine tuning is a kind of transfer learning only. The difference is that in the transfer learning we freeze the early layers, that when the new data from the another domain will come, we will not disturb the early layers because we want those skills as it is. But the remaining portion we will do the retraining. That is most of the transfer learning. A variant of it, fine tuning, in that we say that we will reduce the learning rate. When a new sample will be provided, we will reduce the learning rate. Learning rate is a parameter in machine learning algorithms. Basically, it's called hyperparameter, not parameter. It's not part of the algorithm, but it's the overall training mechanism where we use the learning rate. That how fast you want the things to be learned. So in the fine tuning, we reduce the learning rate, but we don't freeze the parameters of the layers. Okay, even the early layers are also retrained, but the learning is very tiny. We do the minute change in every layer. That's the fine tuning. In transfer learning, we freeze the early layers and only use the final layers to do the training part. Okay, this is actually the part of machine learning and deep learning. So I'm not entering in great detail until unless you guys ask me. So because our whole topic is agentic AI, and this is precursor to that.
Why do we do that in the fine tuning? Why we pause the earlier model? I mean, reduce learning rate.
Huh.
I mean, why fine tune means?
Fine tuning basically means that I will have the learning rate reduced, but will not freeze any of the layers. So I will retrain the entire big deep learning model, but with a smaller learning rate. You may have this question that what basically learning rate means. I have got the briefing from Radha that there are many students, they have already done machine learning course.
Yeah.
So I would like to know from them that what the learning rate means.
Basically, learning rate used in gradient descent, I
Huh?
can say, and it we can
Good.
say we use
So
like
how fast the model
0.01.
is learning on?
How
But
fast model is learning? Okay, good, good.
how fast the model is learning.
Yeah, and what are the drawbacks of it if I increase the learning rate too high?
It misses some like I forget that thing. It misses maybe some data or
All
like
right.
this.
Anybody else who can complete what Rupendra is saying?
I think
Aurobindo, Ankit? Yeah.
I think if we increase the learning rate, the overall accuracy of the model will go down,
Why?
because it will skip learning some important parameters. It will take larger steps to
Good.
complete the entire data set, rather than learning the minute details behind each and every data element in my entire data set. So like he was saying, right, the gradient descent, and also that, I think that is a part of our back propagation, where
Hmm.
we update the weights, right?
Hmm.
So what in the deep learning, what it does is, you update the weight based
Hmm.
on the learning rate. So the new weight would be the existing weight minus learning rate times delta w. So it's the gradient descent. So the change, a minute change in the weight into
Hmm.
the learning rate, to see where my accuracy is improving,
Hmm. Hmm.
so where the loss is reducing. So with a small variation in my weight multiplied by learning rate, if the loss is reducing, that is my new weight.
Good.
And
Very good.
yeah, and so that is what, so the new weight will be the adjusted weight. So this will be my new weight,
Hmm.
which will be used for the next round of forward propagation, or basically the next set of training. So if I am increasing the learning rate,
Hmm.
so that means I am adjusting weights in a larger value. So the next weight is having a huge difference between my previous weight and the new weight. So the descent is very steep. So since the descent is very steep, it might miss the point where it has to stop. So that is what I can get out of it.
Excellent. Very good. Fine. Creating such kind of models which are able to do with the insight that we have to do the transfer learning, we call such models as foundation models. Our GPT, the chat GPT or Grok or Claude, these are all called foundation models. We call them LLM or large language models because they are doing the language related stuff. But large language models are basically also kind of foundation models only. The whole concept of foundation model started only after 2017-18 when the attention mechanism became popular. So moving from the task specific models to the next advancement was deep learning. Because of deep learning, the transfer learning became popular, it became possible. Because the transfer learning became possible, the larger and larger and larger models were created as a base model or source model because their skills can be transferred to other domains where the data scarcity is there. Okay, enough data, collecting enough data is costly or sufficient time is not available, and that particular combination, deep learning with the transfer learning and creating a very large model, we started calling as foundation model. You can see here in this picture. Our large language models, whether it's Megatron, BERT or GPT, they are all foundation models. Foundation models are have multimodality. What does this mean? Multimodality in the sense, I can write text, I can get the text output. I can write text, I can get the image as the output. I can send the image, I can get text as the output. Your model is able to handle multiple modalities. Okay, you give an image, it gives you the text what is there in this image. You give a prompt, it creates a 30-second video. So model is able to do multimodality. That is the next level of progression or the next advancement in the AI, that models are now, these foundation models are basically have multimodality capacity. They are no more the text dependent only. Such models were called foundation model. This term was coined in 2021 by the Stanford HAI department. They basically launched coined this term foundation model in 2021. And since then, several national policies are created around foundation model. There is one more term that was coined frontier models. These are all advancements that have happened in last 10 years. Okay, the deep learning, transfer, fine tuning, foundation model, all of this happened in last 10 years only. Frontier models are basically also kind of foundation model, but they are extremely risky. Risky in the sense they do not care about privacy, security. They do not have any kinds of guardrails. Those are considered as that they can do serious damage. Those are called frontier models. Okay. Ultimately, they are also foundation model. Human-centered AI, that department in Stanford, they coined this term foundation model, and around that they have created national policies. Many other countries are also following the same pattern. Okay. If we have a fair understanding of what this particular thing is mean, then we can go ahead. So far things are clear?
Yes, sir.
Okay. Now, if you don't have the question, then I have some questions. Deep learning is a subset of machine learning that focuses on utilizing the multi-layered neural network. Here is our deep learning. So the outer circle is AI. Then we have inside it is machine learning. Then a specific technique of machine learning is deep learning. And then within the deep learning, we have generative AI. Now, in deep learning is capable of performing tasks like classification, regression, and representation learning. What does the classification mean?
It's like categorizing, objects.
Categorizing objects. Good. And what is regression?
When our output data is like number or like number, we have to, when we give it to model, after that it gives some prediction. After that we give its mean or median, like that.
Okay. Anybody who wants to extend what Rupendra has said?
So regression is predicting a continuous number.
Predicting a
Like
continuous number. Yeah. Yeah.
one
For
point
example, the
something.
sales figure. I have month by month figures are there. I want to predict what is going to be the sales figure. That sales figure could be 100, 101, 101.5, 101.1. There is a continuous space is there. Okay, those numbers are not discrete as in the case of classification, that either is an apple or an orange. Okay, so classification is a more discrete space. In the regression, we have the continuous number space. For example, predicting the height is a regression problem, not a classification problem. Predicting the weight, because there is a continuous space is possible. 5.99 height is possible, 5.98 is also possible, 5.97 is also possible. The continuous space is there, so that's a regression thing. We will come to the representation learning definition. Before that, I have a quiz. Two tasks are given below. Are they same or different tasks? Task 1 is assigning input data to some pre-existing classes. Task 2 is establishing the classes given the input raw data.
Just a different tasks.
Different.
They are different tasks. Why do you think that they are different?
And the one we have given there, the what outputs that will come. Like pre-existing classes is supervised learning. We are supervising that. We give the input and we ask them to give a output based on these classes, the classes we provide. In that,
Okay.
in the raw data, we don't give anything. We just provide the data. It uses it clusters it to it uses some algorithm. So it's falls under the unsupervised learning.
Right. Very good. Who was this? Who was speaking?
Aurobindo. My name is Aurobindo.
Aurobindo. Okay. Very good. So task 1 is basically a classification task. Okay. Assigning a given input data to pre-existing classes. You have fruit, electronic item, or let's say some furniture. A image is given, put it into one of the classes. That's a classification task. Whereas the second task is about finding out the classes. I just have the data, don't have the classes. How can you create classes? That is the second task. First is supervised learning, which is classification task. Task 2 is unsupervised learning, which is called clustering. Here I show you an image. Try to identify that what kind of task is is that, do you see the image?
Yeah.
Yes.
In this image, looking at it, can you see some symmetry here?
Fruits, vegetables.
Okay, fruits and vegetables, that's the classification. That is what the classification we have. We have fruits and vegetable. That's the classification thing we have done, task 1. Is there anything related to class 2 that is possible?
Some are fruits, some are vegetables. Maybe that further segregation needs to be done.
Okay, you said segregation. How are you looking at this image? How do you think the segregation is possible? If I have a pen, let's say I have a pen, how can I do the segregation here?
I mean, yeah, for that learning will be needed. No, I think cut. Some of them are. That is also.
I think it is unsupervised and we will solve it by clustering.
We are forming the, here if you notice in this image, the related things are kept at the same, at the in a cluster. Okay, all cucumbers are at one place, all tomatoes are at one place, all carrots are at one place. That is what the unsupervised learning, that is basically the task 2, finding out the classes. This is tomatoes, this is cucumber, this is carrot, kiwi. So this is task 2. We don't have the classes predefined. We have to create classes. So we do the grouping. This is purely driven, if you just reflect it from the day-to-day activity that we do. If we reflect it, we see that we have been doing classification, we have been doing clustering and classification throughout our life. In the Almira, we arrange things in a according to similarity. The similar things are kept at one side, dissimilar things are kept at another side. Right? This is, and how the intelligence is coming? What is the source of that intelligence? Ability to calculate the similarity. The distance between two objects, the tomato and the carrot, there is certain distance. If the distance is less, if I have another object and that object has a lesser distance, I'm talking using some mathematical terms, lesser distance than the tomato, then I can say that the another object is very similar to tomato. So what I am trying to say is that in our day-to-day life, we have been doing classification, we have been doing clustering, we have been doing representation. I will come to the representation learning almost every day. Thousands of times we have done it. And that same analogy is translated into mathematical space. Mathematical ways are identified, and then the intelligence, as we human have the intelligence, the similar intelligence is brought to the machine. The quiz number 2 has already been answered in our this long discussion. What is the basically the terminology? So first is classification, second is basically the clustering thing. Okay. What is regression? This particular is kind of images, if you have seen this kind of thing, which is very common in stock market trend analysis. Okay, so predicting the continuous numerical values from the input data, this is basically called the regression. In machine learning models like fully connected neural networks can learn complex mapping between the features and the output. Examples are predicting house prices or stock prices using the features like size of the house, location, and the number of rooms. Using that, regression is done. Okay. Now, what is representation learning? The process where a model automatically learns useful features or representations from raw data rather than relying on the manually engineered features. Okay, this is basically a representation learning, that in the raw data, are there any certain features that I can learn that can be used for another task, downstream task, let's say classification. Here if you see this image, what we are learning are basically the representations that are used later on to do classification, that the image that is fed is the elephant.
So how is it different from, there is one more term that I think they had introduced, reinforcement. This is different
No,
from
this is completely different. Yes, there is no, this is basically feature engineering.
Okay.
Or feature engineering, when we do the feature engineering, assume that there is a height column available in an Excel sheet, there is a weight column available, there is a BMI column available, 3 columns are available. Can I create a more meaningful column out of this? For example, if I do height by weight or weight by height, I can replace 2 columns with 1.
Okay. Yeah,
Okay,
maybe using a
more
BMI.
more number of features are there in a given data set. If you have a table of numbers where first column is, let's say, height, second is name, third is age, fourth is location, fifth is email, all kinds of features are available, which is generally case in the enterprise databases. You have customer data, you have customer preferences, so you have columns, lots of columns available in the tables. Out of those tables, for your model, which features are important? That is number one. That is done through we usually do the feature engineering. We drop those features which are not adding any value or which are redundant. We drop those features because they are unnecessarily will increase our computational complexity and will need more amount of data to train the system, to stabilize the system. Okay.
This is called what? Sorry, just can you
Feature
just
engineering.
no, just the whole concept.
Representation learning.
Representation learning.
Yeah.
Okay.
Representation learning is basically also called feature learning, and this is carried out in order to do your feature engineering. So process where a model automatically learns useful features or represents from the raw data. Deep learning excels at this by learning the hierarchical representation, as we noted here in this elephant case. Okay, hierarchy of features are learned basically. Now, how this whole of this background is useful for our LLM, that we have to now we have to connect these dots, and then we have to start our journey about internals of LLM.